Now, with the formal definition of a strip's planning domain, we can now define a strip's planning problem. A strip's planning problem is a triple consisting of three components, and these are given here. This is, of course, the state transition system that we're looking at. This is the initial state, and that is the goal. So what are these formally? The first is a strip's planning domain that is defined over some first-order language we've seen earlier. And again, we have the state space here, the action space, and the state transition function as we've seen in the previous slide. Then there are two more things we need for a planning problem. The first is an initial state, which is simply one of the states in our state space. Finally, the goal of a planning problem is defined as a set of ground literals. And once we are given a goal described in this way, we can define the set of possible goal states as all those states in S that satisfy the goal. And satisfaction was something we defined earlier. You may remember this symbol. We said that S satisfies G if all the positive literals in G are true in S and none of the negative literals in G holding in S. So that is the definition of a planning problem. An interesting observation is that goals are defined as exactly the same things that are the preconditions of operators, namely sets of literals, or for actions, sets of ground literals. That is not a coincidence. And here's a very simple example of a strip's planning problem, a DWR example from the dogworker robot domain. The planning domain is the one we've defined earlier, consisting of the 5 operators described in PDDL. Then I need to pick an initial state, which is what I've done here. So this is our initial state, and I describe that in this expression here as a set of ground atoms. So each of those are relations that relate different objects in the domain to each other. It's a very simple example, as you can see. And then I have to pick a goal, which is a set of ground literals. In this case, I want the robot to be loaded with a container, so it is not unloaded. And I want the robot to be at location 2. These are my two goal conditions. And in this simple example, there's only this one state that is a goal state. And here is a definition of a planning problem in the PDDL syntax. Note that this is a different problem, so it is not the problem we've seen in the previous slide. In PDDL, we of course must define the initial state and the goal, just like we need for any planning problem, but there are a few other things that we need to define. The first thing is we can give the planning problem a name so we can refer to it. That's what we do here. It's a DWR-PB1 problem. Then we can say which domain we're using, and we're saying that by referring to the domain name as shown here. Then we can explicitly define what objects we're using in this domain. This is actually optional and requires the typing extension. So we say that there's one robot, which is of type robot. Then we have 2 locations, 2 cranes, and 4 piles here. And altogether we have 6 containers and the pallet. The pallet is of course also defined in the domain, but that doesn't matter here. So this declares what things exist in our states. Then the initial state contains the ground atoms that relate these objects to each other. So that's what we've got here. We start off with the static relations. These are the things that describe the topology and won't change from state to state. So there's the adjacency between the 2 locations. There is where the different piles are. Piles 1, P1 and Q1 are at location 1, P2, Q2 at location 2, and where the different cranes are, 1 crane at each location. Then we have the dynamic relations listed next, and they tell us what is in the first pile, namely container A, B, and C. Here's the order of the containers on the pallet. Container C is at the top. The same for the second pile. This is also at location 1, containing 3 containers stacked on top of each other, and container F at the top. The piles at the other location are both empty, as you can see here, because the top of the pile is the pallet. Finally, we learn where the robot is and that it is unloaded, and also that the 2 cranes are currently not holding anything. That was the initial state, and now comes the goal. The goal is described as a conjunction, so all of these things must be true, and it's simply saying in which pile the different containers must be. CA must be in P2, CC in P2, and so on, and the other 4 containers must be in the pile Q2. So it doesn't specify the order in which the containers must be in those piles, just in which piles they must be. Note that there are no negative goals in this example, but of course it is possible to define negative goals in general. And if you find this a little hard to read, again, here's the URL where you can find the complete description of this problem, so you can download it and read it in quiet and peace later.